project is part of the Quantum BW bigger project and is funded by the state of Baden-Württemberg. And the talk will be divided into two parts. One is by me from the Fraunhofer EMI, and the second part, or the middle part, will be by my colleague from the University of Freiburg. So first, I want to introduce the use case that I'm going to talk about, because this is not a usual quantum computing use case. What we're interested in is the resilience analysis of critical infrastructure networks. So, for example, in a city, there could be a transportation network, electricity, and communication, and all of these are interconnected. And if one of these fails, then this will also impact the other networks. And in resilience analysis, we define the performance of this network and then look how the system reacts if there are some damages. So, for example, here there are 3 different events where one of these nodes gets damaged, and then this might propagate through the system and the performance goes down, and a resilient system will restore itself, and the time that it takes to do that lets us quantify this resilience property. And since this is a network problem and a combinatorial problem in that sense, we thought that it might fit to quantum computing methods. So we tried so far 2 different methods to tackle the problem. So my colleague will introduce you to the first method, where we try to mimic the infrastructure network by a quantum network. And after that, I will talk about the second approach, which is a bit similar to what was presented just now in the talk before. We just map it to a risk model and then try to use the well-known quantum computation algorithms to solve these problems. So, and with that, I hand over to my colleague.
Okay, hi. So I'm Slav Shitokin, and as Christoph announced, I will introduce to you our quantum network approach. The peculiarity of this approach is that each node of the network we consider is an open quantum system. More precisely, this quantum system contains 3 discrete energy levels. It can be realized by atoms, ions, scalar centers, and other quantum systems. Levels 1 and 2 are standard qubit levels that can be coherently manipulated, for example, by laser pulses. And in addition, each node contains so-called defect level 3, which serves to emulate node disruption. This disruptive event happens when there is a transition from level 2 to level 3, incoherent, irreversible transition with certain rate couple 1. And we also incorporate into our model the possibility of node reparation as a result of another incoherent process with rate kappa 2. So the transition from level 3 to level 1. Another important feature of our network is how nodes are coupled to each other. And this coupling is a dipole-dipole type interaction, which describes coherent exchange of energy between the connected nodes. This interaction couples nodes of which one is excited and another unexcited. And as a result of this interaction, the excitation swaps between the nodes. And now we want to map the evolution of this network onto a quantum computer. And as I said, the incoherent or irreversible processes or non-unitary processes are already at the level of single nodes. And therefore, I will illustrate the method of this mapping by considering the evolution of a single node. So, the density matrix of a single node is described by the Lindblad type master equation. And this equation describes the exponential decay of populations and coherences associated with levels 2 and 3. One can solve this equation exactly, and the evolution operator in this case is a certain non-unitary matrix. And now the question is, how do we implement this open systems dynamics onto a quantum computer? And the answer is well known. Any non-unitary evolution can be rendered unitary in an extended Hilbert space. So we need to attach to our quantum system a certain ancillary system, and then the total system described by this tensor product of the density matrices is governed by certain unitary operators. And then after a certain time evolution, we can obtain the reduced density matrix by tracing over the degrees of freedom of the ancilla. And the important prerequisite for the implementation of this method is the operator sum representation of the evolution. We need to obtain from this operator such decomposition where operators MK are so-called Krauss operators, satisfying certain properties. And once we have found these operators, we can use the results obtained in this mathematical paper in order to obtain so-called unitary dilation of the Krauss operator. And as you see from the structure of this operator, its dimension is twice as large as the dimension of the Krauss operator. And it can be shown that this is the minimal possible dilation for this kind of problem. Then I give you an example. So we have a 3x3 three-level system. Then the Krauss operators are 3x3 matrices, and correspondingly, the unitary dilations are 6x6 matrices. And what remains before we implement this evolution on a quantum computer is to match the dimension of our unitary with the dimension of an integer number of qubits. And this evolution of governed by UK can be implemented in 8-by-8-dimensional matrices. So basically, we need 3 qubits to incorporate this evolution. And with this, we can now decompose our unitary into the basic gates. And an example of the resulting circuit is shown on the figure here. But this is just single node. What happens when we have several nodes? Then the problem becomes much more complicated. And in general, it is impossible to find the Krauss operators analytically. But in some particular cases, in particular for the case when there is only one excitation, we could solve this problem exactly. And in this case, the dimension of the Hilbert space is 5, and correspondingly the dimension of the Krauss operators is the same. From this, we obtain that the unitary dilation is 10-dimensional, and when we extend it to the dimension of an integer number of qubits, we obtain that such evolution can be emulated in the Hilbert space of 4 qubits. And here is the results of this evolution of populations of different levels as obtained from the exact solutions in Mathematica and also by the simulator. And with this, I conclude the presentation of this first approach, and Christoph will continue with another model. Thank you.
Yeah, thank you, Slava. So, right, this was the largest system that we could so far tackle with the first approach. And the second approach is now this, I call it now probabilistic approach. So again, I'll show you some network here and these resilient curves. And this is also a simulation, a classical one, with just some constant damage propagation probabilities. So every node has some specific probability of transferring a damage to its neighbor. And a system like that we can directly translate into this kind of risk model. So in this case now, we don't have any time evolution. So we wouldn't now get these curves as seen on the slide before, but we can only compute specific properties of that and maybe use optimization algorithms as seen in the talk before. And what we can do here is to assign an intrinsic failure probability to every risk item, which would be just on this slide the probability that such a node fails on itself. And we have these transition probabilities. And we can also define an impact for the different nodes. So maybe one of them is more important for the overall performance of the system. So then this node might get a higher impact. And the way to translate it is pretty straightforward. So for every risk item, we get a qubit to represent that. The intrinsic probabilities of failure are just modeled by a rotation. And the conditional probabilities here are represented by conditional rotations. And the rotation angles are just such that the probability of measuring the excited state in these qubits is just the same as the probability of a failure in that risk item. And to make it a variational problem, we can define or add some killer qubits, and from their specific state, we can make some conditioned rotations again. So these rotations now depend just on the state of these killer qubits, so that we can encode different variations of our probability setup. And with just these few steps, we could now already do Monte Carlo simulations of the same system as before. So the results would be exactly the same. But of course, there's no need of just doing the same computation on a more expensive hardware. So that's why we have to go a step further to have this promise of a quantum advantage. So we take this risk model from the slide before and add some more unkiller qubits for a cost quantification. And For example, one could go for a final qubit here that represents a threshold for an impact that we could not accept. So if we think of these curves, this would correspond to some minimal performance where we say, okay, if it goes beyond that, then we have lost the resilience game, so to say. And then we can also do this quantum amplitude estimation, as seen before. And with that, we get the probability of getting into this state of unacceptable impact. And this whole QAE circuit we can use as an oracle for further implementations, for example, in a Grover search that has these variational qubits that we added on the slide before as a search space. Or we could go for some kind of optimization scheme and just use this QAE as an oracle for these other algorithms. So this method here was basically invented by someone else. We first tried to just reproduce their result and are now trying to fit it more to our case, but even the language is basically the same as in resilience analysis, so it's pretty straightforward to adapt this then to our kind of use case. But the problems that we face are the same as in the QAE for other groups. So we now have to ask ourselves which of these approaches is more promising. And we saw several setbacks of both approaches. So, for example, with the networks, the method could only be scalable if we could use these single node results where we find the cross operators analytically. And if we could couple them in some way with one another without having to solve this, these cross operators for the whole system at once. So if we could solve it only for one node and then couple them by some other means, then this might be scalable. One other problem is that we don't start with thinking in quantum circuits. We start by thinking of physical operators in matrix representation, and we depend on these transpilation methods, the automatic ones, and they create unnecessarily large quantum circuits. So I tested it for one very small system where I could transpile it also by hand. So it was very small. And the automatic function gave me a circuit with about 20 C0 gates, and not even a single one was needed. So once these methods are more optimized, maybe our circuits get also a bit smaller, and then we could also see results on the real backends. And also for this method, it was straightforward to begin with this kind of approach because it's a quantum network, so you would consider it a good example case for a quantum computer, but there is no algorithm involved from that we know it could yield a quantum advantage, because there are very few of them, as you know. We would have this kind of promise with the second approach if we use this Grover algorithm, for example, in the end, then one might get this quadratic speedup in the end. But on the other hand, in this approach, we have the problem with these large circuits. It's even worse than for the network method. And also, we don't get the full time evolution that we would normally like to have in resilience analysis. So here we would somehow define different questions that we could answer with this method, which can also be a feature, but one first has to find the interesting questions that can be tackled with this. And with this question, I thank you for your attention.